This week we'll start by identifying sources of existing time series data and preparing data that was not originally designed for time series analysis. The first repository that we can look at is the UCI Machine Learning Repository. The initial repository was created as an FTP archive in 1987. When you expand View All Dataset, you will notice on your left panel time series data type with about 99 items. Feel free to browse and review some of the available dataset and try to identify attributes denoting time sequencing. You may also notice some potential challenges. Data may have incomplete timestamps. For example, in a dataset absenteeism at work, the time columns are limited to month of absence, day of the week, and seasons, and you do not have a column for a year. Of course, there are duplicate time indices, but we also have a column indicating employee identity, so we can differentiate between these duplicate time points. Time axis can be horizontal or vertical. As an example, you can look at American Sign Language dataset, where there is no timestamp column, and the actual time is represented as a sequence of steps forward. Another challenge is varying notion of time units, whether it's by day, by month, or timestamps including minutes, seconds, or just a year. The second repository is UEA and UCR Time Series Classification Repository, and it provides time series data for research specific to classification tasks. And it was created in 2002 by researchers from University of East Anglia and University of California, Riverside. And now it's about 130 dataset. They're all diverse in types and formats. You can find images, sensor data, simulating data. If you're not familiar with dataset formatting, let's review a couple of important terms. Here we have ARFF format. This is the attribute relation file format. So dataset can be exported as ARFF files, can be exported as a text files, or scikit-learn specific TS files. So univariate versus multivariate format. Univariate analysis deals with only one quantity that changes over time, and the main purpose to describe patterns without any cause or relationship. For instance, you can have only one variable or column called height that is measured as a sequence over time. If you have two variables, we're dealing with the bivariate data. In multivariate, data involves three or more variables, and we're interested to see relationship or causality between them. The US government provides a variety of time series data for decades or even collected over centuries. Climate data is available at the National Center for Environmental Information. The Bureau of Labor Statistics publishes a monthly index of national unemployment rates and other information about employment. In the domain of health, we have CDC, Center for Disease Control and Prevention. It publishes weekly flu case counts, for instance, during the flu season, mortality rates, disease rates on national, state, and county levels. And finally, for economy, we have the Federal Reserve Bank of St. Louis, which provide economic time series data. How do we create time series data? To create time series data from any structured data, we need some sort of timestamp indicators. And here's a few examples of where we can find timestamps. So any record with a time and date, for example, the time when the transaction was recorded or the web click occurred. You can model the delta time between timestamps so that the time series would consist of time on your temporal axis and the delta time on your value axis. And then you can even aggregate this delta times as mean or totals over larger periods. In some cases, time is not explicit in data. And you can think of data as a distance versus value, where the distance will be one of your axes. It could be order in relationship, such as wavelength, and the second axis will be your value. Another way to obtain timestamp data would be to look at scientific discipline records of physical traces, where these records, this time series actually store in a different format. It could be an image file, could be a single vector with a single field of a database. A good example of creating time series would be typical event type or state type SQL data. Here we have 3 tables: email recipient behavior, a membership history, and donation history. So we can look at certain questions, for instance, email recipient reaction to emails over time, a membership history, whether there were periods where a member let their membership lapse, and transaction history, when does an individual buy, or can we predict this? These 2 examples show different timestamping convention or even different level of granularity. You may notice time variables display as year, yearly member status, date, a weekly record of email open, and date timestamp of donations. First, we can downsample the donation data to turn it into the weekly time series that will become comparable to the email data. And second, we'll record all relevant time periods, even if nothing happened. So we'll add those records, and we'll add also zero counts, because 0 is also informative. This is what it looked like, a time series created from 3 different SQL tables. So we aggregate donation by weeks, and we expand record for each new timestamp, also by weeks. Right, time to review some time series terminology. When a variable is measured over time or at a fixed interval, the data become a time series. And historical time series is when observations are collected over fixed sampling intervals. What is sampling intervals? Or sampling frequency or periodicity? It's how often observation or records occur. And you can find exactly evenly sampled data, approximately sampled data, and even data with missing points. We also use statistical approach, in which the historical series treated as realization of sequences of random variables. A sequence of random variable at fixed interval is discrete time stochastic process. Of course, you can use a shorter name time series model. Let's represent our time series of length n by x at the time t in a curly brackets. So n is our length, t is discrete time, and we have sequence of random variables x1, x2, up to xn. X bar represent a sample mean for our time series, which is sum of all events of all x, i's over the length of time series. And head notation is used to represent a prediction or forecast. And forecast is a predicted future value. And it's important to remember that the future value is the time t plus k, and k is the lead time or number of steps into the future. So our forecast at time t for a future value at time t plus k. Many time series are dominated by a trend and or seasonal effects. A simple additive decomposition model is given by observed time series at time t, which is equal to sum of trends, m at time t, seasonal component s at time t. An error term in general is a sequence of correlated random variables with mean 0. And if you look at the plot decomposition, which you will be doing this week, you'll notice there are 4 subplots. So we have observed value, x at the time t, observed time series at the top. We have trends, seasonal component and random component, which is error terms. If the seasonal component tend to increase as the trend increases, and you can notice in the plot where the fluctuation is increased, multiplicative model instead of additive model is more appropriate. So we have m at the time t multiplied by seasonal component at the time t plus error terms. There are several methods to estimate trends. The m trend at the time t can be estimated by a moving average centered on xt. And moving average? It's an average of a specified number of time series values. For monthly time series, we have 12 months. So to calculate m trend, we need to find a moving average. If we denote January as a time t equal 1, and December as a time t is 12. Our average, in fact, is 6.5, so it's a month between June and July. And we have issue here because we do need an integer. We need a specific month or t event. Solution for this problem is to use t1 as a January and add t13 as a January. Both of them will be using a half 0.5 weight. So when we sum, our average will become 7. Then we can estimate a monthly additive effect, which is S hat, by subtracting our moving average from time series at the time t. With the estimate of monthly additive effect, we can calculate seasonally adjusted time series, which you probably have heard and seen specifically in governmental data when, for instance, unemployment rate is provided, seasonally adjusted and non-seasonally adjusted. So to create a seasonally adjusted time series, we just have to subtract S bar average seasonal estimate from our xt at the time t. So for smoothing, we can use two methods. We can use centered moving average, an example of smoothing procedure that apply retrospectively to time series, with objective to identify underlying trend. And of course, smoothing has some disadvantage because we have some points missing at the beginning and at the end. Another smoothing method is LOS, a weighted regression technique.